Hi, this is going to be a presentation about semantic vectors and their application to user research. So to give a flavor of where I'd kind of like to end up with this presentation, so imagine you're in a situation where you've done user research, you've got maybe a lot of users, and you've asked them as part of your research to pick a word to describe some service you're evaluating. Now, what do you do with all these words? Say it's free choice. One thing you could be interested in is seeing where those words lie on a kind of scale or spectrum from one extreme to another. For instance, bad to good, mistrust to trust, or boredom to excitement. Could there be a way that you can quantify that? And once you can quantify that, so you can put maybe a score or multiple scores on each of those words for every participant, then you can start doing statistics. So you maybe want to see whether certain groups have different scores on these scales, or maybe you want to look at a correlation between those variables and something else you've measured. So could you do that in some automatic way that gives you that number? Also, you could consider, well, maybe you've got those data, you've done some analyses, and you have a client, they say, well, actually, I've thought of something else I want to look at. Now, is there a way to do that via the computer so you don't have to do that manually? Now, that kind of analysis is made possible by semantic vectors. So what I want to do in this presentation is give an introduction to what they are, how they're created using machine learning, and a little bit about how they're related to human cognition and associations. And as we go along, I'll mention some ways in which they might be useful within user research. Just a quick note before continuing, some of the slides that are going to be coming up are going to show you apps which will let you play around with semantic vectors. What I'd suggest doing is following along as I explain what those apps are doing and try to explain what the inputs and outputs are. But of course, it's probably going to require a bit of hands-on playing around with these apps to really understand what's going on. If interested, at the end of this presentation, there's a slide with links, and that'll give you a chance to go off and try things out. What you could do is go back to the relevant slides in this presentation and then try to replicate what's going on there. So to get started on trying to understand what semantic vectors are, these are basically just lists of numbers that represent the meaning of words. So there's an example of an illustration here, not a real one, but you could take the word happy, and in this imaginary example, the meaning of the word happy is represented in the 5 numbers. It's a list of length 5 or a vector of length 5, and those numbers are -2, 1, 3, 0.5, and 3. Now, the point of that is that you could have a different word, for instance, joyful, and look at its vector and compare that pattern with the pattern for happy. So in a fake illustration here, joyful has a similar pattern to happy. So that you can see that for every element in the vector, they have kind of similar values. So the idea is that similar meanings means similar vectors. And then the opposite of that is that opposite meanings have opposite vectors. So for instance, what you'd expect to see is the word sad having kind of the reverse direction of values in its vector. Now those were made up examples. So the question is, well, where would you get such vectors? So as we'll see in a little while, hopefully it's quite useful to have that if you can have them. But yeah, where do they come from? So the method involves a neural network, and that learns to predict patterns of surrounding words for each word in a vocabulary. And the idea is that the patterns of words around words being the same means those words mean kind of the same. So we've got a little mini exercise here. Apologies if it feels a bit childish maybe, but just to get the idea right. In the 2 boxes, we've got a list of sentences that are associated with a particular word. And that word is now hidden. It's an X on the left and a Y on the right. So if you take a couple of seconds to scan through those sentences and think, well, what could X and Y be? So 5, 4, 3, 2, 1. So as you probably guessed, those words are something like lion and tigers. So what you can see is that there's something similar about lions and tigers, because you can kind of interchange those words in the same kind of sentences. Now for background, I think it's maybe useful to have a little bit of an idea of where those vectors come from in a bit more detail, because as user researchers, you're probably not going to be training this network yourself, although you could. It's all actually very available, but maybe you're using a pre-trained network. But it's still good to understand, well, how does that network deliver these semantic vectors in the end? So without going into too much detail about how neural networks work, because I'm kind of assuming that you've heard of them before, you know that the activation spreads throughout the network via the connections, depending on the weights of those connections. The interesting thing here is the structure of the network. So this has an input layer, and the input layer consists of basically the words in a vocabulary. So you have a big long list of words. For instance, that could be 3 million words that are being trained, and a word being present in a sentence basically means that one node in the input layer associated with that word is activated. And if we then look at the output layer, this is what the network has to predict, and that's the pattern of words around that input word. So in the example we saw, when we see the word lion, we expect there to be a certain pattern, a certain set of words that are more likely to appear in the output layer. And the neural network has to learn that. So if lion is activated, we expect the network to say, I think words like fear, prey will be activated at the same time. And then the magic happens in the hidden layer, in between the input and the output layer. And the thing here is that the hidden layer will have a relatively small number of neurons. So you could have millions of words that are all represented in the input and output layer, and they're all funneled into a hidden layer of typically 300 nodes. And now what those 300 nodes have to do is somehow efficiently represent those patterns that the network has to predict. So if we run that through for instance, the word lion again, the word lion is going to have 300 weights that connect that one word to the hidden layer. Then that hidden layer is going to have the same connection of weights to all the words, and the output layer represents the patterns. So that doesn't change. So the thing that does change is if you see the word lion, then that word lion will activate a certain pattern in the hidden layer via the weights that the network is learning, and those patterns in the hidden layer are going to be expanded out into predictions for the probability for each word in the vocabulary to appear around the word lion. And this is where it gets good. Thank you for following along so far. It's been a bit abstract, I can imagine, but this is the point of it. This is where you get your semantic vector, because the semantic vector is nothing other than the weights that connect the word lion to the nodes of the hidden layer. There are some variations in how you can build these networks, but that's the basic idea of it. Now, the word tiger is going to have its own 300 weights that connect that word to the hidden layer. And the idea is going to be that those weights from tiger to the hidden layer are going to be somewhat similar to the weights for lion. And then to sort of hammer the point home, take a completely different word like mineral. The word mineral is also going to have 300 weights connecting that word to the nodes of the hidden layer. And those weights aren't going to be very similar to the weights for lion and tiger. So as mentioned, the details of how you train that network might not be directly relevant, but you have to be aware of it. The network is going to be trained on some corpus, which is the word for a set of texts with a whole bunch of sentences that are used to train that network, to make that network predict those surrounding words for each word. The Google News corpus is a very well-known one. This is publicly available. So they've pre-trained their semantic vectors on the Google News data set. So there's 100 billion words in there. They use 3-dimensional vectors, and they've got a vocabulary of 3 million words and phrases. So you can just access this, download it, and use it for your own purposes. But of course, it's kind of obvious, but nevertheless very important. What that network produces in terms of semantic vectors is going to completely depend on the corpus. So the method by itself doesn't do anything. It's always the method in combination with the corpus that gives you particular semantic vectors that you subsequently want to use. Now, for a moment, assuming we have a successful translation of words into semantic vectors, that opens up a whole bunch of new possibilities, because once you have vectors, you have all the operations you can perform on vectors. So you can add them, subtract them, they have angles, you can do all sorts of things with vectors. And then the big question is, if you accept that those vectors do somehow capture the meaning of words, can you then get meaningful operations by applying standard mathematical operations that you can do to vectors to those specific type of vectors that come from these neural network models? The simplest kind of operation you could do on vectors is adding and subtracting. What that means is you take all the elements of one vector and you add or subtract those values to or from the elements of another vector. So it's element-wise. So in this example, just to get that idea clear, all it is, in this case, you've got two vectors and they have a length of 3. So they each have 3 elements. So the one has 10, 6, and 10, and the other one has 3, 2, and -5. And if we add those vectors, take a few seconds, what numbers do you expect to appear in the vector that's the addition of those two? So 3, 2, 1. And then, as you probably expected, you get the new vector 13, 8, 5. And that's the vector that is produced by adding those other two vectors together. So then, kind of surprisingly, what happens if you add and subtract semantic vectors seems to capture what you expect to happen based on the meaning of those vectors. So there are some kind of classic examples coming from Mikolov et al., who developed this method. And again, we'll do this in a tiny little exercise. The first example is what happens if you take the vector king and you subtract the vector man and you add the vector woman, right? So what do you think that means? And the second example is if you take the vector Paris, you subtract the vector France, and you add the vector Italy. So what do you think you get in those two cases? So I'd suggest, have a little think, and we'll see whether that's all making sense. So 5, 4, 3, 2, 1. So as you probably guessed, what you get from doing this with these vector operations is a vector that's similar to the word queen and to the word Rome in these two cases. Because if you take the word king and you kind of take away maleness and you add femaleness, that makes sense that that's then the queen. And similar to Paris as the capital of France, if you take away France and add Italy, you get the capital of Italy, which is Rome. Now, to make things a bit more concrete and to show you how things work in code, I'll actually run through an exercise with semantic vectors. So looking at that example that we heard about from this paper. So what you're seeing here is Google Colab. So you can get into this for free, and you can use that to program and play around with all sorts of machine learning things. I'm using something called the GenSim Toolbox, if you're interested. So you can look that up on Google and get all the information about that. It's very, very nice toolbox, easy to use. So I've loaded that. I've loaded the Google News semantic vectors, and now we can play around with them and see, do things work the way the existing literature says they work. So what I've done is I've assigned the vector belonging to the word king to king vector, and the same for man and for woman. So I'll print out that vector so you can see what it actually looks like. In all its glory, here we have the 300 numbers that represent the meaning of the word king in terms of semantic vectors. So what we can now do is we can do this bit of addition and subtraction we talked about that we think should give us queen. So we take the vector for king, subtract the vector for man, add the vector for woman. And then we have a function that's going to give us the vectors that are most similar, or the words that are most similar to this vector in terms of their semantic vector. So let's have a look at what this gives us. And then shockingly, if you don't get queen as the best one, we still get king. So king is kind of still winning even though we've taken away man, added woman. Queen comes in second, which isn't bad. But what we can now do, which I think is also kind of interesting, we can think about, okay, can we use the maths of vectors to boost the effect we want to see? So this is a little bit disappointing, right? So I really want to see queen here. But what if I like take off double the man vector and add double the woman vector? So I'm kind of, supercharging the gender effect by doing a bit of vector algebra on this in this little operation. And then it turns out that we do get queen, because I've sort of emphasized with this really simple, simplistic, but yeah, we can not do man minus plus woman. We can do 2 times man plus 2 times woman, and then we get queen as the top word. Now, the next thing we can do with vectors is we can calculate their similarity. So this is what we were doing more intuitively before, with these illustrations of the similarity between the vector for happy and joyful, which you can see here on the left, and the dissimilarity between the vectors of happy and sad. I'm not going to go into the details of that one. There's something called cosine similarity, which is used a lot, and this is based on sort of basic geometry of vectors. But the practical point is there's a way that you can precisely measure the similarity and precisely define it on a -1 to 1 scale. So what we have now is a way to measure kind of the association between concepts. So if we have 2 words, we could say, well, are these words similar in terms of how this network understands the meaning of the words? And in psychological terms, you could say, well, that's sort of like an association. So we associate words together in memory. We might even have biases around which words we associate with other words. And the idea is that vector similarity might capture that. Again, this isn't an assumption. This is an empirical question, and it's been tested. And Kadiskan et al. In 2017 published a paper in Science that showed that, yes, if you train the network on a particular corpus, you'll see that the biases that people have that went into what they wrote are represented in the network. So with Kadiskan et al., they looked at sort of neutral as well as problematic associations. So there are classic examples in psychology of things you just associate with other things. So insects and flowers are associated with being nasty versus nice. But unfortunately for AI, but interestingly and importantly for research purposes, we also see things like racism and sexism hidden in the associations in the network as represented by vector similarity. There's also some research looked into biophilic associations. So the biophilia association hypothesis is that human beings have a sort of natural affinity for nature. So you'd expect that the words in networks are associated with positive words related to well-being, and that was found as well. Of course, the network doesn't care about nature, but we do, and it's represented via how people write about things in the semantic vectors. To further emphasize that these semantic vectors actually do have something to do with what's in our brains, there's even research that shows that you can use semantic vector associations or semantic vector similarities to predict reaction times on tests of associations, of unconscious associations in humans. So there's reason to think that, yeah, there's something there. There's some correspondence between vector similarity and the associations we have between words. So with that, we can start doing some interesting things that at least, maybe make sense. So one of the things we could think about is, well, what if we have a list of words and we want to analyze what those words are associated with? So in this case, this is a little bit of software that lets you do that. We have a list of target words, in this case, angry, furious, satisfied, joyous, and depressed. And for each of those words, we want to get a sense of what meaning they're associated with. Now, you can do this in a load of different ways. Sentiment analysis generally means good versus bad. That's the valence of words. but we don't have to stick with that. So I've called that sentiment analysis plus. Of course, you can check loads of associations depending on what your research aims are. In this case, it's valence, just for illustrative purposes. So the positive words here: good, positive, healthy, happy. Negative words: bad, negative, diseased, and sad. Right, so we're going to check whether each of those words is associated with the set of positive words versus a set of negative words. Leaving, again, details aside for now, but hopefully the idea is clear. And the results of this are given here. And what you can see is that the negative words have this negative value, which represents the similarity, the vector similarity between that word and those contrasting sets. And positive values means there's a sort of average positive similarity or average similarity with the positive words versus the negative words. And I'll send you a link that you can play with this on the website just to see how well it works. But you can imagine that, hey, this could be a useful thing to do if you want to automatize a lot of values, or maybe if you want to use a method that doesn't depend on what you want to be true, anything like that, you could consider using this kind of technique. As a second example of sentiment analysis plus, imagine you're working with some kind of anti-crime charity, and this charity does anti-crime interventions, and they want to evaluate their effects. What they might be doing is, before and after the intervention, they have all the participants fill in a questionnaire, and one of the things they do is ask them for a word that they associate with the word gangs. So what they'll have is some idea of the shift in attitude they want to achieve in this intervention. So there'll be an attitude that they expect participants to have before they go in, and they want to have them to have an attitude that they think is going to benefit them afterwards. And for instance, that attitude beforehand might be represented in a set of words to associate with gangs, like safety, being an adult, being cool, being strong, or being confident. Just an example, right? So this would be part of the research you do to kind of decide, what set of words represents that positive pole of an attitude. The negative pole is going to be defined by a set of words which are bad, which are negative in the valence sense as well, but are specific to what they want to achieve with this intervention. So they might be aiming for associations with gangs like stupid, dangerous, going to prison, being a criminal, or being weak. Just examples, right? So now we have two sets of words, and this is going to define our scale. So this is going to be what the positive and the negative pole of the values are if we run this semantic vector analysis. And then what we'll do, we'll just get, again, this is imaginary, we'll get the imaginary words that were filled in by participants. So for instance, the words after the intervention, and you could add words as the contrast in this case, which would be the ones they picked before the intervention. But for now, to keep it simple, let's say this is a set of words you want to analyze. So what we'll do, we'll click submit, and then what it will do for each of the words they've entered, so one participant in this case, is going to put a score on those words that reflect how much does it go towards the positive or the negative pole of the scale that we've created. And what that will do, it'll give you those values that you can subsequently use for further analysis. So what you always have to do is check things. So are we getting sensible values? Is it doing what we expect? So we can see that the word cool is getting a positive value, which means it's towards a positive pole, which is what we don't want. So this is someone maybe that didn't really respond to intervention. But the next person said, well, I associate gangs with being dumb, and this has a nice negative value. Ignorant has a negative value. Independence had a positive value, which is correct. We want independence that would be On the wrong side, in this case, would still be quite a positive association. And then we've got stupid, cowardly, wrong. They all have nice negative values. So what we're seeing here in this case is that the meaning of the word in terms of the spectrum that we've set up is indeed giving us values that we expect. And you could then do your statistics and run your tests using these values. And give a second application, you can also use vector similarities to kind of tag different words or sentences. So in this case, the input of a little app is a list of sentences, and for each sentence, we're going to check via vector similarities if a particular one of a list of tags has the most similarity to words in that sentence. So in this case, there's some sanity checks. So some of the words are the same in the sentences and the tag list. Let's just check whether it's working. But there are some interesting ones here and here. So we have the sentence, we had a party for my birthday, and you have the sentence, I went to the funeral. And then we've got the tag words, celebration, angry, happy, fish, grieving, and fridge. So we don't have the literal same words, but you can imagine that, well, there's a kind of obvious option. There's a kind of obvious meaningful tag for each of those. So if you have a party for my birthday, that's sort of about celebration more than any of the others. If you say I went to the funeral, think, well, that should have something to do with grieving. And it turns out, if you look at the similarities, you can indeed get that correct tag. So the best tag of those for we had a party for my birthday is celebration, and the best of the tags for I went to the funeral was grieving. So again, what you do with this in, for instance, user research depends on your creativity and of whether that makes sense in the context, but there is a possibility there. One of the things you could consider doing is not even looking at user data. It's kind of heretical to say, but there's an option there, and just say, well, maybe there are situations when it might make sense to say, well, let's look what happens kind of in the machine, so within the network. The reason you might want to do that is, for instance, to generate hypotheses that you then go out and test with actual users or participants, or maybe you want to find a way to use efficient stimuli in some kind of paradigm that you want to launch. But you've got a lot of choice of which words you want to use. Maybe there's a way to use existing associations if you've got them from a relevant corpus to maybe boost the effects you find in a study, right? Not to falsify it, but just to use to test your null hypothesis in an efficient way. And that the reason you can do that, again, from the previous slides, there's at least some correspondence between what you find in those models and actual human associations. So of course you have to be very careful with that, but there is some reason to think, hey, maybe this is useful. And of course it's much more efficient to do it that way than actually going out and having like 1,000 people answer a questionnaire or do an interview, do a psychological task, where you could say, well, actually, let's just see what we see in the data. It doesn't give you behavioral evidence at that point, of course, right? But you can do things like, hey, I expect some kind of association. For instance, in the biophilia hypothesis, I expect an association between nature and well-being, but what exactly? That might not be so clear, that might not be defined in the theory. So you could say, well, let's look at the words, specific words involved in nature, like forests, rivers, fields, and let's look at specific well-being words like calm, happiness, confidence, and then check which of those associations we find in the model. And maybe that gives you a bit of a clue or a bit of direction on how to proceed further. For instance, again, stimuli for a task. If you don't have time or the resources to do work with actual people, maybe that's the best you can do for the time being. And what that could look like, and there's an app you can use to do this, where here we have 3 target words we're interested in, so beer, wine, and coffee. And you can say, well, I want to test whether each of those words is more related to a set of positive words than to a set of negative words. In this case, the positive words are hungover, tired, and drunk. The negative words are awake and alert. Positive and negative doesn't mean good or bad in this case, it just means plus or minus. And then we can do a little statistical test, which gives you a p-value based on randomly selecting words from your vocabulary. And then you can see in this case that beer has a significantly stronger relationship between the set of positive words versus the negative words, which isn't the case for wine or coffee. Now, this is the final example of things you could do with mathematical vectors that you might want to also be interested in doing with semantic vectors. That's cluster analysis. The idea of cluster analysis is you might have a whole bunch of vectors sitting out there in some like high-dimensional geometric space, but they might be clumped. So a whole bunch of those words might be sitting close together in space and far away from another clump. And it might be interesting to see what kind of groups are there. And if those vectors we're clustering are semantic vectors, we're looking potentially at words with similar meanings, right? So you might have a big long list of words, maybe taken from a questionnaire or from previous analysis or a transcription, whatever it is, things people have written down on sticky notes. And could you use semantic vectors to say, well, what does the machine tell me the groups are? So it's kind of a quantitative affinity mapping you can do, again, automatically, and with all necessary caution. So there's an example here where we've got a bunch of words. So dog, cat, hamster, rabbit, skyscraper, house, building, bungalow, angry, happy, sad, furious, and joyful. And then the question is, well, if we take the semantic vectors for all those words and we check whether they cluster, how do they cluster? Right, so you can play with this and test whether it works the way you need it to or expect it to, right? So in this case, we get 3 clusters. One cluster is angry, happy, sad, furious, and joyful. One is skyscraper, house, building, and bungalow. And one is dog, cat, hamster, and rabbit. So in this particular case, it's not always going to work, but in this case, yeah, it does pick out those 3 types of meaning. So we've got emotions, buildings, and animals, or pets. And then you go into the same situation where you kind of interpret what those clusters mean, how could you use them, and so on. Getting towards the end of the presentation, so hopefully you've got a sense of what semantic vectors are, where they come from. I think that's kind of automatically shown also where the risks are in using them, but also maybe the potential. The 3 examples that I've given that relate them to user research, just to remember, are sentiment analysis plus, tagging, and quantitative affinity mapping. It might be interesting for groups who've listened to this presentation to do some discussion amongst yourselves. I've got some questions which might be interesting as a sort of kickoff. One thing you can think about is, well, how does this relate to LLMs or AI in general? So of course, there's a lot of talk about large language models currently. One point is, well, there's similar risks, obviously, because semantic vectors sit in LLMs. So all the problems you have with biases and inherited stereotypes, of course, also sit in LLMs. But there's also, I think, something more for user researchers, which is about the relationship of yourself as a researcher to the method you're using. With an LLM, people use these LLMs in a way that maybe risks replacing what they should be doing themselves as a researcher, their own kind of thought process. You're kind of offloading a large amount of thinking and decision making and evaluation to the model. Whereas with semantic vectors, it's much more constrained. It's really saying, well, I've got a method that assigns a value to a word. I've decided what that value means. I've done my little calculations with the vectors. I understand what the neural network behind it all is doing, even though I didn't train it myself. But I'm really on top of things. At least, that's one way you could see a difference there. Of course, I think my bias is clear, but it's maybe something to talk about. A second point, there's obviously quite a lot of discussion about, the qualitative versus quantitative approach to research and user research. You might think that semantic vectors are inherently quant. Depending on what you mean by that, that's not necessarily the case. For instance, you can be very explorative with semantic vectors. For instance, if you think about the clustering, there's no test there. You're seeing patterns. You're still going to be very interpretative about what's going on there. But you can also use it with the mindset of, well, I want to be very strict about how I'm testing things. I want to kind of take out any bias I have out of the equation at the point of testing, even though you can never fully avoid it. But at least you could say, I'm going to make my decisions beforehand, then see what the method tells me. So this is like the statistical way of looking at things. So maybe there's an interesting thing there is about, well, does this really commit you to a particular philosophy of research? Another point to think about is, well, how much work do you need to get to use semantic vectors? So say you're interested in this, you'd like to use it, but how do you get there? Because you usually don't start off with just a bunch of words, which is where semantic vectors sort of live. But there are lots of additional processes, data processing methods, analyses you can do that might be necessary to get from your research question to this kind of analysis. So if you're interested in that, you can look up natural language processing, which covers much more than just semantic vectors. And finally, the thing to wonder is, well, will clients understand what's happening, and will they value what's happening when you're given results using this kind of machine learning analysis? So I think that's also something to think about. Does it, and maybe overawe some people, or make them less critical, or in other cases, will they be overly critical? Will that depend on your particular audience? So those are some questions to get started with.